Playing against a computer is only fun when it's challenging, let alone beating a human player at chess. I'm excited to tell you all about some of the most popular algorithms behind game-playing computers, one of the many exciting areas of artificial intelligence. In this course, we'll go over some of the techniques implemented by Deep Blue, the IBM computer that defeated the chess world champion Garry Kasparov back in 1997. You'll also get to see these techniques in a fun implementation of the Cat Trap game developed in Python. Plus, you'll have the chance to play around with the code. So welcome to the course. I'm sure you'll find these clever tricks interesting. This course is designed to give you an idea of the high-level concepts behind game-playing algorithms. So before we get started, please be advised that there are some requirements to make the best out of the course. First, this is not a beginner-level course, so if you are new to programming, please consider taking an introductory course from our library, like Foundations of Programming Fundamentals, which will give you all the tools you need to get algorithms into code. Second, all of the code examples you'll see in this course are written in Python 3, so you should feel comfortable with this programming language. If you are not experienced in Python, I recommend that you consider taking an introductory course like Learning Python. And lastly, for our examples, you'll need the NumPy and PyQt5 packages, so you should have them installed before proceeding. Once you are okay with these requirements, you may go ahead and start the course. Before we talk about the Deep Blue chess-playing computer, let me tell you about supercomputers. You may already know this, but to succeed at the challenge of beating a human chess champion, we need way more computational power than just a desktop computer. So, supercomputers are computers with much higher performance specs than regular desktop computers. They usually have many CPUs in blocks known as compute nodes, which perform massive parallel computing. They also have huge specs for storage and RAM. All of this computational power comes with a price. Supercomputers are very costly and highly demanding in energy and space. As examples of supercomputers, I can mention those by Cray Research. This picture shows the HLRN-3 Cray system at Zeus Institute in Berlin. So what are the applications of supercomputers? Well, supercomputers have been used for weather forecasting, aerodynamic research, astronomy, biology, pharmacology, and most of these applications involve highly demanding simulations. In addition, supercomputers have been used to tackle problems by brute force, where computation would take too long on a regular computer. The picture shows a Blue Gene supercomputer by IBM. Now let me tell you some interesting historical details related to Deep Blue. Deep Blue is a chess-playing supercomputer that was developed by IBM with the purpose of winning against a human player, a big milestone at artificial intelligence at the time. The development of Deep Blue started at IBM in 1989, coming from an earlier project from Carnegie Mellon University. After countless hours of research and development, Deep Blue finally defeated the chess world champion Garry Kasparov in a series of matches between 1996 and 1997. So, what was the software running in Deep Blue? Well, Deep Blue admittedly used a brute force approach, and as you'll see, this is not necessarily bad. Furthermore, one of its developers even denied having used artificial intelligence at all in Deep Blue. Today, however, all of the techniques used by this computer are considered part of the numerous tools in AI. To be more specific, Deep Blue ran a variation of Minimax, a tree search algorithm. Now, about hardware. Deep Blue had a special architecture designed to implement some form of the alpha-beta search algorithm, which you'll see in this course. The technical specs include a mainframe computer, massive parallel computing, and custom processing chips. But a more significant detail is that it could process 200 million games per second. If we compare this rate of computing with modern computers, I'm happy to report that today you can get this processing power from a smartphone. However, remember that this was a supercomputer back in 1997, when cell phones weren't smart at all. And today's supercomputers are much, much more capable than today's smartphones. When you want to develop an AI agent that plays a game, it's important to keep in mind the type of game you are going to play. Games can be classified according to a number of properties. First, we have the number of players. There are zero-player games like bingo or snakes and ladders. Yes, there are players in these games, but they aren't really active and the game progresses by chance regardless of their actions. A very well-known one-player game is solitaire. There are two-player games like chess. Some games may have many players like poker. And we have massive online games as an example of unlimited player games. The availability of information divides games into two categories. Complete information games, like chess or tic-tac-toe, where all players can see the state of the game at all times, and incomplete information games, where information is hidden to some players, like auctions and poker. Chance is another way to categorize games. There are deterministic games like chess or Go, where the intended moves are always achieved. And there are stochastic games like backgammon and poker, where the moves are determined by some random event like throwing a dice. Games may also be turn-based, like reversi or poker or chess, or they may be concurrent, like rock, paper, scissors, or pretty much any sports like soccer or basketball. So here's the type of game we are interested in. That is to say, the type of games where the techniques in this course apply very well. We're interested in games that involve two players with complete information, deterministic, and turn-based. For example, these techniques apply to chess, checkers, tic-tac-toe, and the cat trap, which is the game you'll see showcased in the programming examples of this course. To play a turn-based game like tic-tac-toe or chess, we are going to use a tree-based decision-making approach. This technique consists of predicting the outcome of all possible player moves starting at the current state of the game. In this algorithm, we must choose the move that yields the best result for us. Be aware that running this algorithm produces only the next move, not the whole sequence of moves in the future. So this is how tree-based decision-making looks like. Take tic-tac-toe for example. Let's say the game is about to start and it's our turn. We have the X mark and the opponent has the circle mark. In this first step, we have 9 possible moves. We can place our X mark in the top left, top center, top right, all the way down to the bottom right square. Now notice how this is creating a tree structure. The ellipses mean that I'm not showing further states horizontally or vertically. That's because this tree will get really, really big. So, for each of these second-level states, our opponent has 8 possible moves. So, for example, for the leftmost child, our opponent may place his or her circle mark in the top center, top right, middle left, all the way down to the bottom right square. This branching is going on for all siblings of the second level. In the next level, it's our turn again, and we get to place our X mark in 7 different squares. You may imagine that this branching of the tree keeps going until there are no moves left, or until one of the player places 3 marks in a row. So the main objective of this brute force algorithm is to help us choose the move in the root of the tree that maximizes our chances of success. Although we try to see into the future for all possible games, we are only going to get a recommendation for the next single move. That means that to play an entire game, we have to use this brute force algorithm for each turn of X. Now let's briefly talk about the complexity of this brute force approach. Notice that the tree for tic-tac-toe grows with a large branching factor at the beginning, and this branching factor goes down because less moves become possible as the game progresses. So at the first level of this tree, we have to analyze just one state of the game, the current state. Next, we have 9 places where we can place our mark. Then the opponent has 8 options, then we have 7, and so this number goes down one move at a time. That's why the total number of games we'd have to evaluate to produce the first move in tic-tac-toe is 9 factorial, which is a bit over 360,000. That's not so bad. Pretty much any desktop computer, tablet, or smartphone today is capable of computing this whole tree in less than 5 seconds. And there are even better news. This is a pessimistic estimate, so we may aim for an even smaller number. Let me show you why. In our example, let's pay attention to the second level. Here we have 3 states that are equivalent if we rotate the grid. So these are rotations of the same state, which may be examined just once. In the next level, I'm showing 2 states that are equivalent after a rotation and a reflection. At the bottom level, let me show you one more state, which would be a rotation of an existing state at that level. So here we have seen equivalent states from rotations and reflections. Let's see another scenario. Suppose we have these 2 cousin states and it's X's turn. Here are 2 children of these states that aren't just equivalents because of a rotation or reflection. They are the same state. And finally, let's move on from the leftmost state to a terminal state where X wins. If we naively count all possible moves, we would include illegal states to the count, such as this one, which would follow the victory of X. With all of this in mind, our estimate may be refined to discount post-winning illegal states, and the count would go down to about 255,000. And if we are clever and discount duplicates, rotations, and reflections, we may make a nearly tenfold improvement. Because of these reasons, tic-tac-toe is among the category of solved games, meaning that the strategy for playing perfectly without ever losing is already known. You may draw, but never lose. So a search algorithm is not needed for tic-tac-toe. Now, how about chess? Well, chess is a very much more complicated game than tic-tac-toe, and certainly not a solved game. Let me give you an idea of the complexity of chess. Consider a game that ends after 40 pairs of moves, 40 for white and 40 for black. A pretty accurate estimate is 10 to the 40 possible games. So how long would this take to compute? This is where the fun begins. Imagine a computer that is capable of processing a whole game of chess in 1 nanosecond. By game, I mean a state in the search tree, a chessboard. This is very optimistic because today a computer may be expected to perform a single operation in 1 nanosecond. An operation like an addition or a multiplication, not checking all 64 squares in a chess game. But let's dream. So in this computer, producing one move would take 10 to the 40 nanoseconds. That's about 300 times 10 to the 21 years. Okay, let's dream some more. Your computer probably has somewhere between 2 and 8 CPU cores, which crunch data in parallel. So let's dream about a computer with 1 million CPU cores, which would give us a speedup of 1 million. That computer would still take 300 times 10 to the 15 years. Well, this doesn't seem very promising. So how long is 300 times 10 to the 15 years anyway? Let's put this number in perspective. The Earth is believed to be about 4.5 billion years old. The universe is estimated to be about 14 billion years old. And finally, this is how long the algorithm would take to produce one move in the supercomputer. Now remember, this is overly optimistic. We're only considering reasonable moves with 1 million instances of a CPU that takes 1 nanosecond to process a whole chessboard. If we want to use this technique, we must do better than that. IBM was aware of this back in 1989, but they had some cool tricks under their sleeves. So keep watching and you'll see that there is hope. In the programming examples of this course, you will see an intelligent agent that plays the cat trap game. So the first thing I want you to do is to get acquainted with the game. So by all means, Google it and play it. This game works on a hex grid, which is similar to a beehive where you have hexagonal tiles, and you play against a cat, taking turns to block his way out. If the cat can't move, you win. If the cat reaches an edge, you lose. Let's take a look at the game. Here we have one implementation of the cat trap game. As you can see, it works on an 11 by 11 hex grid, and the cat is always at the center tile. Notice that there are some blocked tiles at the beginning of the game, and these are random. So let me show you a new game, and another, and one more. So now let me show you how I play against the cat. And I want you to pay attention to the dynamics of the game and how we are taking turns. So it's my turn, and I have to block the cat by selecting one tile. Let's say I select this tile right here. The cat has made his move. So I will keep on trying to block the cat, and you'll see how clever this cat really is. I think I caught the cat. Yes, the cat is trapped. Now all I have to do is block him so that he has no way to move. Let me block this tile, and this one, and this one. There you have it. I won. But you may want to try your hand at the cat trap game, and you'll see that it's not that easy. Let's give it another shot. And right now I am about to lose. The cat got away. So there you have it. I don't think this implementation of the cat trap is actually using the techniques we'll see in the course. The techniques we will see will guarantee that the agent will play optimally. However, you'll see some difficulties to this approach. Now here are some additional details about the cat trap game. First, this is a special type of turn-based game. And I say this because the two players have different rules. As you could see, the cat is trying to escape, while I'm trying to trap the cat. In other words, my options for the next move come from the set of free tiles in the grid, while the cat has only at most 6 possible moves. It's neighbor tiles. And like I said, we will make an intelligent agent for the cat. This means that our intelligent agent will try to maximize the utility of the cat, not the utility of the player. The Python setting for the cat trap consists of 3 source files. First, we have cattrap.py. This file contains the implementation of the graphical user interface and the logic for the game. It also contains some controls for you to choose which algorithms to use. Throughout the course, I will only show you some parts of this file. Next, we have hexutil.py. Now this is a library that contains functions that allow us to print a hex grid. We will not go through this file in the course. However, you may want to skim through it just to see what's going on. Now the third file is catgame.py. This is where you'll find my code. And as you may expect, this is where we'll spend most of our time. Now please be advised that I will only show you some select parts of the code, the relevant parts to the algorithm at hand. So please have this file handy to read it slowly. So let me show you how the cat trap game works in this Python implementation. As you can see, the game runs on a window, and we have several controls at the right. Let me show you what those controls do. First, we have a button to start a new game. This game will be started with a hex grid that has the dimensions in the first box you see with a number 7. First, we have a button that says Start New Game, and this will start a new game with the dimensions in the first box. As you can see, this box has a 7, so the new game will be on a hex grid of 7 by 7. Let me show you. So as you can see in the console, we have a message that says New Game Started, hex grid dimensions 7 by 7. Now let me show you how to play. So I will make some moves and the cat will make some moves of its own. But first, let me set this deadline to 1 second. As you can see, when I hover around the tiles, they will become shaded. And when I click on a tile, I will make a move. Let's say this one right here. Notice that the terminal showed the state of the game as a matrix, and the tiles are represented with a 0 if they are empty, with a 1 if they are blocked, or with a 6 where the cat is located. For now, all I want to show you is how to play, so I will make another move, and the cat made another move. Let's try one more. And the cat is about to get out. So the cat won. Finally, I want to show you a nice feature called the edit mode. At the bottom, we have a checkbox that toggles this mode. So let me enable the edit mode. And now I get to toggle the state of the tiles or to move the cat. Let me show you. You can modify the state of the game as much as you want at any point of the game. You don't have to interrupt a game, and you don't have to reset a game. Now let me show you how to move the cat. You just click on the cat, and then you click on the new location. When we disable the edit mode, we can resume our game. I'll tell you about the remaining controls as we move forward. So, as a warm-up, let me show you the simplest intelligent agent we can make. It's not so intelligent, it's a random cat. But first, let me show you how the code works. First, in the graphical user interface, we are calling our functions with the mouse press event in line 142. Let me scroll down. And from lines 206 through 211, we have the assignment of certain flags that come from the checkboxes in the controls in the graphical user interface. Now, in lines 206 through 211, we have some flags that are set by the checkboxes. And these checkboxes configure the algorithm we want to use. Now, in line 213, you'll see that we have two variables, new I and new j, which are the new cat coordinates. These coordinates come from the custom cat function. This is a function that will use the algorithm we chose with the checkboxes. This is where we go to catgame.py. Now this custom cat function starts at line 61 with a lot of comments. Here you'll find what the arguments are and what the return value is. You'll also see how to use this function. You don't have to change anything. So there are a few details I want you to pay attention to. First, in line 83, we set up a deadline which comes from a text box. This is the timeout in seconds for a cat that takes forever. So in this deadline, you are supposed to place the longest time you are willing to wait. Next, you'll see that all of these flags determine what is assigned to the result variable. In other words, which function will be used to respond. And in line 90, we have the random cat. Finally, in line 99, we report how long it took for the cat to respond. Let's see the random cat function. So as you can see, this function starts at line 107, and the first thing we do is call the valid moves function. Now this function will return a list of identifiers for the valid moves of the cat. So these identifiers are strings. They could be W, E, SE, SW, NE, or NW. These are the valid directions in which the cat may move. In other words, the legal moves. So these identifiers stand for west, east, southeast, and so on. In this implementation, I'm printing those moves. And finally, if there are some valid moves, I will randomly choose one move to return in the dir variable. If there aren't any possible moves, we will return the same cat's location. That's how we give up, and that's how we report that the cat has lost. So to return the chosen move, we have to apply that move. And all we need is the new cat location. So in line 117, I am calling the target function. That target function takes in the cat's location, those are cat I and cat J, and it needs a direction, which will be west, east, or any other of those directions. So we can expect this function to return the new cat's location, which will be random, but it will be valid. Let's see it working. Let me run the cat trap. And I will use the default 7x7 hex grid, but for a random cat, we need to check this box. So now let's see the cat moving randomly. If you look at the console, you'll see all of the valid moves the cat has seen every time I make a move. So it should be very easy to trap this cat. There you have it, I won. Now the difficult thing is to lose to this cat, so I'll have to show this cat the way out. There you have it. So as a final note, checking this random cat checkbox overrides the rest of the algorithms. And the deadline is not so important because a random cat won't take long anyway. The main algorithm our intelligent agent will use to produce its next move is called Minimax. And that's because it minimizes the opponent's maximum payoff, which is to say, it minimizes your own maximum loss. This trade-off is due to the fact that we will simulate an opponent who wants to beat our intelligent agent, maximizing his or her payoff, and an intelligent agent who wants to beat the opponent, minimizing the opponent's payoff. Minimax is a tree-based search algorithm that performs a depth-first traversal for search. And you'll see that this is almost a completely brute force approach. Let me show you an example for you to get a good idea of Minimax. Let's suppose we have a game with an initial state represented by a triangle pointing up. Let's say that this is our intelligent agent's turn and that it always has 3 possible moves. In this case, I've named them A, B, and C. These moves will produce the ensuing states of the game now shown as triangles pointing down. At this level, it's the opponent's turn. Now the opponent also has 3 possible moves, which will produce the third level states now shown again as upward triangles. These represent our agent's turn, each with 3 possible moves once more. Now these options will produce states where the game ends. The values shown represent the final score. Now this is a zero-sum game, which means that our loss is our opponent's gain. So when these numbers are positive, it means our agent won. When they are negative, it means our opponent won. 0 represents a tie or draw, meaning that neither has won. Naturally, we want the largest positive score we can get. And our opponent wants the largest negative score possible. That's what the triangles mean. I have labeled the levels of the tree at the left, starting at level 0, and at the right, I've labeled the role of each of these levels. The top level, level 0, has only one node in which we are trying to maximize our score. This is known as a max node, and it's represented by an upward triangle. In level 1, our opponent is supposed to make a decision, so we assume that the opponent wants to minimize the score towards a negative value. That's why the nodes at this level are minimizing nodes, or min nodes, which are represented by downward triangles. At level 2, we have max nodes again, and so we have max nodes for our agent's turn and min nodes for our opponent's turn. This goes on until we have terminal nodes. Be aware that not all game trees have a constant branching factor, nor do they always end at one specific level. This example was designed for convenience. So, as you'll see shortly, each min node copies the most negative score obtained from its possible moves, and each max node copies the most positive score from its moves. This has to happen from the bottom up because only the terminal states have scores. Finally, at the top, the algorithm picks move A, B, or C, whichever yields the most positive value. So let me show you how Minimax works on the tree we just saw. The only argument we need is the current state of the game at the moment we are called to produce our next move. This is the top min node. Now, recall that Minimax operates in a depth-first traversal. This is the order of evaluation you'll see in this example. We'll go from left to right. Recall that we have 3 possible moves, A, B, and C. So the agent is going to decide which of these 3 moves minimizes our maximum loss, or in other words, which of these moves will yield the best result for us. Since this is a max node, we are going to choose the maximum of these 3 options. So we start by analyzing move A. This produces a new state in a min node, which in turn has 3 possible moves. Notice that to choose the minimum value here, we need the values, so we need to dig deeper. Starting at the leftmost move, which takes us to yet another max node. Again, we need scores, so we keep on digging. This is the depth-first search nature of the Minimax algorithm. Finally, the first move we analyzed in level 3 is a terminal node, which yields a positive score of 1. The next one yields -2. And the third one yields 9. So since level 2 has max nodes, we choose the maximum from 1, -2, and 9, which is 9. Notice that we're only interested in the score. Knowing which move results in that score isn't very useful because we're only projecting the game into the future. We're not making that move yet. Now that we have the first value for the min node at level 1, we are ready to explore its second move. So we once more produce a new state in a max node, and its resulting scores are 0, 4, and 3, the maximum being 4. Now for the third move in the min node, we have outcomes of 5, 2, and 8, which is the maximum. Notice that now we have all the scores needed by the min node to choose the minimum value, which is 4. Great! Now we have the first value for the top max node. In the same order as for the whole subtree of move A, we'll propagate the values up for move B. Bear with me as I show you the whole subtree and propagate those values afterwards. So, from left to right, we'll get the following maximum values. Between -2, -1, and -8, the maximum is -1. Between 5, -9, and 3, the maximum is 5. And finally, between -7, -8, and -9, the max value is -7. So now at level 1, the min value is -7. As you can see, we're not very interested in move B so far. Move A looks way more enticing. Now, let's see the same chain of events for move C. Remember that this will happen in a depth-first fashion from left to right. So now we choose the max values into level 2. These are from 8, 2, and -7. The max value is 8. Now between -6, 2, and 0, the maximum is 2. And between 9, 8, and 7, the max value is 9. The min value for level 1 is chosen from 8, 2, and 9. So the score is 2. And now we are finally ready to choose the best score and to return which move will give us that score. So between 4, -7, and 2, the best score for us is the most positive, and that's 4. Now the move that produces that value is move A. This is the only step where we are interested in knowing which move to use because that's what we are supposed to return. This is a decision problem, and this decision comes from an optimization. The scores are important, but the expected result is a move. Now let's see the pseudocode for Minimax as seen in the celebrated book, Artificial Intelligence, A Modern Approach by Peter Norvig and Stuart Russell. First, recall that we use Minimax to produce a move, or more formally, an action to take next at a given state of the game. But Minimax is an optimization algorithm that produces a number, a score. So the decision algorithm for Minimax is just a wrapper for the function that implements the top max node. So in line 1, we have the declaration of this Minimax decision function, which takes a state as argument and returns an action. Line 2 calls the function that implements the max node decision. This function is called maxValue, and as you can see, it takes the same state of the game as argument. The result of this function is the score chosen by the max node, and it's assigned to a value variable v. In line 3, we return the action among the successors or children of the current state that has the value returned by max value. So now I have some good news. You don't have to worry about building or maintaining a tree because this happens automatically by means of recursion. So here we'll see two recursive functions, maxValue starting at line 1 and minValue, which we'll see shortly. This maxValue function receives a state of the game and it returns a utility value, which is the maximum score from its successors or children. So the exit condition or base case for this recursive function is shown in line 2. If the current state is terminal, it means there must be a score. So we return that score by calling the utility function for that state. Then the recursive part is very simple. Since we want to find the maximum value, we initialize a value variable v with -infinity to indicate that anything will be greater than this value. Next, in line 4, we produce a list of all possible actions from the current state, and we will run a loop for each of these actions. In line 5, we update the value of v to the maximum between its current value and the min value of the child state that results from applying move A to the current state. Yes, the min value function is the implementation of min nodes. Finally, we return v, which is to say, we return the maximum among the children's scores. This is very memory efficient because we are exploring each child at a time. That's why v is accumulating the maximum value. This means that at any given point in time, this function will analyze at most one child state under it. Now, for the min value function, starting at line 8, you may want to pause the video and notice how this function is almost identical to max value, but it works in the opposite direction. It seeks to minimize the maximum utility. So the recursion happens as these two functions call each other until a terminal node is reached. As you can see, the algorithm is quite simple. Since we've already seen a scary scenario for these algorithms, it's important to get a sense of how well our algorithms will work. So let's talk about the complexity of Minimax. Suppose we have a search tree with a constant branching factor b and a maximum depth m. In other words, each state has b possible moves, and the game goes on for m turns. Well, the time complexity of Minimax is O of b to the m, and its space complexity is O of m. Now, this is asymptotic notation, so these are not exact expressions for the running time or the memory needed by the algorithm. Instead, these expressions refer to an upper bound of how the running time or the memory requirement grows as b or m grow. As you can see, the time complexity is exponential, just as you might have expected. Minimax takes billions of years to produce one move. This is because at each level, we have b more possible states to analyze, and this will go on for m turns. Increasing m by 1 makes the tree b times larger, but increasing b has a much more dramatic impact. Now, for the space complexity of Minimax, things are looking pretty good. It's O of m. It's not just proportional to m, but exactly m. This means that the maximum memory required by this algorithm is a nesting of m function calls. It only needs to analyze m games because, as we can see, at any given point in time, we are only going to examine one game. Once min value or max value returns, it frees the memory it occupied. The priceless advantage here is that the branching factor has no power over the space complexity of Minimax. Think of our original chess example where we considered 40 moves for white and 40 moves for black. The expected time for this example is outrageous and totally unacceptable. However, its memory requirements are extremely modest. We only need enough memory to go 80 levels deep into the tree with only one game per level. Even for an excessive case where 1 megabyte is required to analyze one chessboard, this algorithm would require just 80 megabytes, which is not a problem today. Now I want to show you very briefly how my implementation of the Minimax cat works. First, in the custom cat function, we get to call the Minimax function only when none of the checkboxes is selected. That's the default algorithm. So let's go see that function. As you can see in line 123, this is just a wrapper for the Minimax function. But notice that it returns two values, the move and a placeholder I'm not using. This placeholder contains the value of the best move. Remember that we are not interested in the value of the next move, but rather only in the next location of the cat, which is the move variable. That's what we return. Remember, this is the decision problem, not the optimization problem. So let's see the Minimax function. This function is at line 296, and as you can see, it is a wrapper for the max value function. You may have noticed some extra arguments there. Those are useful for the implementation of some optimizations you'll see ahead. So let's take a look at max value. And here we have it. So the first time we call max value, we are sending -1, -1 as the move we want to perform. So in line 238, we are checking for that specific move. If we are not making that move, then we have to make the move that was sent as an argument, and we do that in line 240 by calling the function apply move. Now notice that we are applying this move on this game object. But this game object was assigned a copy of the original upper game at line 237. That's because we want to modify the game. We are building a new node with a new state. So just like the algorithm we saw in line 242, we get all legal moves for the cat. Remember, these are west, east, and so on. Then we check if we are at a terminal state, in which case we ultimately return the utility function. That happens at line 246. Yes, it has some adjustment I'll tell you about later. Next, starting at line 250, we have the for loop. And the most important part is the recursion performed by calling the min value function. Next, starting at line 263, we have the min value function. You may want to take a minute to compare these two functions, and you will see some slight differences. These are due to the fact that the cat has some rules and the opponent has some different rules. Let's see this Minimax cat working. So this is where the deadline comes in handy. Right now I have a deadline of 5 seconds. If the cat hasn't responded in 5 seconds, my game will delete the cat, making me win by default. Let's see. First I have to configure the Minimax algorithm, so I have to uncheck all of these checkboxes. Now we are ready, and I will make one move. After 5 seconds, the cat will give up. So there is no cat anymore, and when I make my next move, I will win. So what happened? The cat took too long. It actually would have taken years. So to actually show you a cat that uses the real Minimax algorithm, I have to produce a very, very small tree. So this is what I like to call a perfect cat in a small world. Let me change the dimensions to 5. And let me modify the game. There. This cat will produce a very small tree, but it will play perfectly. It will not make a mistake because it will use the Minimax algorithm, which plays optimally. So notice that this cat has 3 options. It may go to the left, it may go down, or it may go up. But notice that the path that goes up has 2 options. So that's the best path. If I block the left or the down paths, this cat has to make a move up, because that way the cat is guaranteed to win. So let me show you. I will block the down path. The cat went up, and now there is no stopping this cat. If I block the right tile, the cat will get out through the left tile. And if I block the left tile, the cat will get out through the right tile. So let me show you. The cat got out, no matter what I do now. Now notice that this worked only because I blocked most of the tiles. Let's see with this game how we do. As you can see, we got a timeout. So sadly, A perfect cat can only play in a very, very small game. We still have that billions of years problem. So a first attempt to solve it is called alpha-beta pruning. It's based on the observation that when analyzing a min node or max node, some options can't possibly be the min or max value we are looking for. So these options can be safely left unchecked. Now, remember that an option in the Minimax tree is a subtree that can be pruned off. So our hope with this pruning is to get rid of a lot of unnecessary work. However, the task still seems uphill. Do you think we'll be able to shrink 300 times 10 to the 15 years down to something reasonable like 10 years? We'll see how well alpha-beta pruning actually does a little later. For now, let me show you how it works. Consider the same example we used for Minimax. I will guide you through the whole process again, but this time we'll follow the alpha-beta search algorithm. Now, for the left subtree, action A, we'll follow the whole process. And then we'll fast forward a bit for the subtrees of actions B and C. So first we analyze the left branches until we reach a terminal node. So now that you know how Minimax works, notice how the min node at level 2 gets a partial result. So far, the maximum value it has seen is 1. This value is not final. The next value is -2, which is less than 1, so it doesn't update the partial max value. And the next is 9, which updates the max value in level 2. Now we're done with all 3 moves, so the max value of 9 is finalized at level 2. This value is in turn affecting the partial result of the min node in level 1. The next max node in level 2 examines the values 0, which is the highest so far, then 4, which now becomes the highest so far, and finally 3. So 4 is the final max value, updating the min value at level 1. The rightmost move is where the pruning starts to happen. First, we get a value of 5, which becomes the highest so far. At this point, this max node at level 2 is aware of the best value its parent node at level 1 has seen. This best min value is called beta, and its value is 4. So think about this. We are currently evaluating a max node, so its value can only get higher than 5. But our parent node will pick the minimum value among our sibling nodes, and it already has 4 as a candidate. Therefore, there's no point in looking further at this max node. This is where we prune off some branches. Right now, we have skipped 2 nodes to analyze. This finalizes the value of the max node at level 2. So the min value for move A at level 1 is finalized at 4. The same happens at the top level. 4 becomes the maximum value it has seen so far. This number is known as alpha. Now let's fast forward some steps in the middle subtree. At this point, I've propagated the max value of -1 from level 2 into the partial min value at level 1. But look, it's time for some pruning again. Notice that the top max node has seen a max value of 4 so far. So anything less than this alpha of 4 is reason enough to stop checking at the min node in level 1. The reason is that checking more values will only reduce the min value in level 1, so we are sure it's not going to be chosen by the top level as a replacement for alpha. So we might as well stop now. Notice that we've pruned off 2 subtrees. That's 8 nodes off our to-do list. That finalizes the min value of -1 for move B at level 1. Now let's fast forward again in the subtree for move C. Once again, we have a tentative value of 8 at level 1. So we may prune off options that change this value to anything less than alpha, our best max value so far, which is still 4. The middle move produces 2, which is less than 8, thus modifying the min value at level 1. But wait, this value of 2 is also less than 4, so we are done checking options at level 1. We've pruned off yet another subtree with 4 nodes. This again finalizes all of our values, and we can safely choose option A. Now let me remove the pruned off nodes so you can appreciate how the tree has slimmed down. Here's the pseudocode for the alpha-beta search algorithm. This is pretty much the same as the Minimax decision algorithm, a wrapper for the top max node function. Now notice that max value takes 2 more arguments than its Minimax version. These arguments are alpha and beta, with initial values of -infinity and +infinity respectively. These values tell our algorithm that it starts knowing nothing about the values it will eventually choose. So formally, alpha is the best max value reported by the parent node. Initializing it in -infinity means that the first value we consider will be the best so far. Conversely, beta is the best min value reported by the parent node. This is initialized at +infinity for the same reason. Now, here's the alpha-beta version of max value. If you look at the code, you'll see that it works just as the Minimax version of max value, except that it does 3 things with alpha and beta. The first usage of alpha and beta is in line 5, where the usual maximum is calculated to update the value of v, our best value so far. But look at the min value function call. It's sending the values of alpha and beta to the children nodes, so they will be aware of the best max and min values so far. The second usage of alpha and beta is in line 6, where the value returned by the recently examined child node is compared to beta. If it's greater or equal to beta, it means that checking the remaining children is pointless because it's already greater than the best minimum so far. In other words, it's not eligible as a replacement for beta, and the remaining children can only make this worse. That's why the function aborts in this case and returns v, knowing that it will not update beta in the parent node. The third usage of alpha and beta is in line 7. If we are still here, we update the value of alpha because we want to communicate this best max value to the remaining children nodes. Finally, here we have the pseudocode for the min value function. Similar to the case of Minimax, this function looks almost identical to max value, except it operates in the opposite direction. Again, you may want to hit pause to go through the code. For now, I will just point out that in line 6, we are comparing the newly found value to alpha and aborting if it's less or equal to alpha. This is because checking the remaining children would not make this node eligible to update alpha. So what's the improvement we can expect from Minimax to alpha-beta search? Again, suppose we have a search tree with a constant branching factor b and a maximum depth m. While there is an improvement in time complexity, it is not a certainty. So we can get anything from no improvement to an improvement from O of b to the m to O of b to the m divided by 2. And its space complexity stays at O of m, because we still have to go all the way to the deepest level at least to produce the first min or max value. So what's the meaning of this best case improvement from O of b to the m to O of b to the m divided by 2? Well, it's not at all significant if we want to reduce billions of years to some minutes, but it does have a very interesting effect. Dividing m by 2 means that we would be able to go twice as deep with alpha-beta in the same original Minimax time. In other words, if we run alpha-beta search and Minimax in two identical computers simultaneously, by the time alpha beta finishes, the Minimax computer is halfway through the tree. This will come in handy a bit later. Now be aware that this is the best case. Sadly, the number of pruned off branches is highly dependent on the order of evaluation. The good news is that you may achieve a reasonably good ordering by using a policy that prioritizes certain types of moves. For example, you may check the most aggressive moves first, then defensive moves, and you may leave avoiding moves for last. That said, there is still good news. Even a random order of evaluation usually results in significant pruning, meaning more levels to compute for the same price. Let me show you my implementation of the alpha-beta cat. So the custom cat function takes the alpha-beta pruning algorithm from the AB flag. And you can see that this is used in line 97. Once again, only if AB is selected, we will use the alpha-beta cat function. Notice that this AB flag is also used in lines 92 and in line 95, because alpha-beta pruning can be used with the other optimizations of the algorithm. So let's fast forward to the alpha-beta function. Once again, in line 130, we have the alpha-beta cat function, which works just like the Minimax cat function. And the alpha-beta function is in line 384. As you can see, the function call works pretty much like the Minimax call. Once again, we are sending a move of -1 to the first call. And the function we call is called AB max value, for alpha beta pruning max value. Let's look at it. As you can see in line 314, this function is doing pretty much the same thing as the regular max value function, but it takes into account alpha and beta. So where are those values used? You can see them in lines 334 in the recursion, also in line 341 when we check for the value of beta, and finally in line 343 when we update alpha. Let's see if we can experience the improvement of the alpha-beta pruning algorithm. So let me set up the same perfect world. But I will complicate this world. Notice that it has 2 more tiles available. This causes the tree to expand a lot. So let me just set this up for playing with the regular Minimax algorithm, that is, no checkboxes checked. And let me make a move. Let's say I block this tile. The perfect move would be to go up. And we got a timeout. Now let me do the same thing, but now I will use alpha-beta pruning. Notice that I have checked this box. So let's make the same move. And the cat made the perfect move. This way it cannot lose. So let me try and block him. And we are done. The cat won. Now, although there is a very little improvement with alpha-beta pruning, you could see it working right here. We saw the Minimax algorithm fail with a timeout, and the alpha-beta pruning algorithm provide a solution in the allotted time. So let's stop for a moment and ask ourselves what's stopping us from doing better. Well, complexity. Minimax inherently runs on the depth-first search tree traversal algorithm, so it's really impossible to do the whole thing significantly faster. But wait, the fact that we cannot find a perfect solution to this problem in a short time doesn't mean that we cannot find a reasonable solution in a short time. This has been the key enabler to useful AI we are using today, like traffic apps or self-driving cars. A solution produced in a short amount of time doesn't have to be bad. So with this in mind, we could make some compromises. For example, we could prune further by identifying and skipping states that we've already seen. We could even push this to identifying rotations and reflections of already seen states. We could also reduce B, the branching factor, by selecting the, say, 3 most promising moves, while leaving unproductive or self-harming moves unchecked. And we could reduce M, the maximum depth of the tree, by stopping early at some level X of our choice. And this is what depth-limited search is all about. For example, let's say that we intend to stop at level 2 if we haven't found a terminal state yet. This would leave us with a 3-level tree. But we have a problem here. How are we going to get the values for these bottom nodes if they aren't terminal nodes? Some of them may be terminal, and earlier level nodes could also be terminal, but for the most part, these will be interruptions of the Minimax algorithm. And the problem is that only terminal states produce reliable utility values. So here's the compromise. Instead of perfect score predictions, we have to come up with an estimation of these values and settle for that. At each bottom level that's not terminal, we have to evaluate the game and come up with a score that measures how good we are doing, how much we would like to be at that state. We need to assess that particular state of the game. This is where intelligence is coded into the algorithm. The quality of the game playing agent relies on the quality of this evaluation function. So to implement depth-limited search, you need a simple modification to the Minimax or alpha-beta algorithms. Here we have the max value function for Minimax, but the modification has to be done to the min value function as well. So the addition is in line 3, where we compare the current depth to the maximum depth we want to explore. There are many ways to maintain the depth variable, so I'm leaving that open. Sometimes it's a function parameter, while sometimes it's a single class member or even a global variable. Back to line 3. If we are at that depth and this is not a terminal state, notice that we check for terminal states in line 2, then run the evaluation function on the current state and return that value. This will ultimately leave us with the tree we want. Notice that by reducing the depth of the tree, we are hopeful to get a solution exponentially faster. So a 40-level tree may take billions of years, but maybe a 5-level tree will take 10 minutes, and a 4-level tree will take 1 minute. So here's what depth-limited search does. We select a constant level at which we wish to stop the search. And this will leave us with a very valuable smaller tree. Notice that we will not analyze most of the original tree, and that's fine. The running time for the algorithm on this tree depends on the level at which we are willing to stop. So some trial and error may help us decide this level. However, this improvement in time comes with a cost, and this cost is accuracy. At the bottom of this smaller tree, we need a good evaluation function to estimate how well we'll do if we take the paths underneath these bottom nodes. If we use a poor evaluation function, our agent will behave poorly. Remember that Minimax produces the best solution possible, so that's the best we could aim for, and we must be ready to have a less than perfect agent. In order to minimize these imperfections, we need to come up with a good evaluation function. Here we have 3 important details to keep in mind when writing a good evaluation function. First, it must order terminal states just like a utility function would. This means that an evaluation function must give a higher score to better terminal states and lower scores for worse terminal states. In our algorithm, an evaluation function wouldn't be required to analyze a terminal state because we check for terminal states before looking at the current level. But it's a good practice to put your evaluation functions to the test with terminal states. and they must be able to tell a better outcome from another. Second, a good evaluation function must return quickly. Remember that the whole point here is to speed up the process. It wouldn't make sense to take a very long time at the evaluation function. In fact, the ultimate evaluation function is the Minimax algorithm. So it is possible to implement an evaluation function with Minimax, but that's exactly what we are trying to avoid. And finally, a good evaluation function must return an estimation of the actual chances of winning. Now let me show you some examples of evaluation functions for different games. My objective is to get you to think and to motivate your creativity. Let's start with chess. Let's say it's white's turn, and we want to assess how this game is going for white. An evaluation function may calculate the difference of the piece count for white versus black. Since white has 11 pieces and black has 9, this evaluation function would yield 2. This positive value means white is winning. Another evaluation function could be the piece count ratio, calculated by dividing white's pieces by black's pieces, which is 1.22. Here, a value greater than 1 means white is winning. We could calculate the shortest straight line distance from any of white's pieces to black's king. This doesn't sound very strategic, but that distance happens to be 3. We could also revisit any of the piece counting evaluation functions, but with weights assigned to different pieces. So pawns may have a weight of 1, while a bishop may weight 6 and the queen may weight 12. Now these functions are just simple examples that wouldn't accomplish much in a real agent. Over the years, countless evaluation functions have been described by experts in different games, but chess is by far one of the most widely studied. So one or a combination of some of these expert functions may be suitable. Here's another example, this time for reversey. In this game, you flip two-sided round pieces which may show a white or black side on top. There are 2 players, white and black. The objective is to flip your opponent's pieces by surrounding them with 2 of your pieces in a straight line, diagonals included. So for this game, let's suppose it's white's turn. A simple evaluation function may calculate the difference of pieces again. This would yield -3, which suggests white is losing. The ratio would be 2 divided by 5, or 0.4. Again, a value less than 1 means white is losing. We could also count the number of next moves for white. As you can see, there are 5 possible moves for white. Alternatively, we could use the largest gain possible among next possible moves. As you can see, this move would yield a gain of 3 white pieces. Similar to chess, reversey has a history of research and techniques you may want to look up. A very popular pencil and paper game is dots and boxes, where 2 players take turns in placing horizontal or vertical lines in adjacent dots in a square grid. Every time a player completes a square between 4 adjacent dots, this player places his or her mark in this new square box and has an extra turn. In this example, player A has placed 2 boxes and player B has 3 boxes. Let's suppose it's A's turn. The box difference evaluation function would yield -1, indicating that A is losing. The box ratio function would yield 0.667, again indicating a bad situation for A. Now, the number of harmless moves may be an interesting evaluation function. Any of these 4 lines wouldn't give an immediate advantage to B, so 4 moves would be harmless. If you are experienced in this game, you may have noticed that being A's turn, this is an opportunity for A to score some boxes. So another evaluation function may measure the largest gain possible by taking 1 move and taking all ensuing extra turns. As you can see, this move yields 4 marks for A. Once more, All of these evaluation functions are just examples for you to get a sense of how complicated the design of evaluation functions can be. So now that we have depth-limited search to pretty much take as long as we can afford to respond, is alpha-beta pruning still relevant? After all, recall how unimpressive the improvement of alpha-beta pruning was. At best, it reduces the exponent to its half, meaning that it reduces the running time to its square root. To put this in perspective, it would reduce 1 billion years to about 32,000 years. That's not so impressive. However, recall that splitting the exponent in half also means computing twice the levels in the same amount of time. So in the best case, if we use regular Minimax with depth-limited search on a tree of some depth n, and it takes, say, 1 minute to compute, then, by simply adding alpha-beta pruning, we could compute a tree of twice its depth in that same minute. So the upshot is that we get to compute deeper trees. And why is this good? Well, because evaluation functions are usually far from accurate, and their accuracy improves with depth. It makes sense. The deeper we go into the game, the more informed our evaluation function, thus the better our choices. Now, I've been mentioning that splitting m in half, thus being able to go twice as deep, is only the best case. So for a tree of depth n, we get an added depth of n, which means the same amount of computed gains while going twice as deep. But what about the average case? Well, the average case for a random order of evaluation of moves is still a very good improvement of about 1/3 the original depth. That is to say, if we were originally able to go 6 levels deep, by adding alpha-beta pruning, it would take the same amount of time to compute the same 6 levels in the unlikely worst case of no improvement at all, or 8 levels deep for the average case, all the way up to 12 levels deep in the best case. So in conclusion, adding alpha-beta pruning to your algorithm is very simple, and it adds a negligible overhead compared to the improvement it provides. If you're feeling up for a challenge, here's an opportunity for you to code some of your intelligence into the cat. Your task is to write an evaluation function. Remember, it must assess how the game looks for the cat because we are running Minimax from the cat's perspective. It must return higher, more positive values for better estimated outcomes, and lower, more negative values for worse outcomes. And finally, a warning. Whose turn it is when we call this evaluation function actually matters. Simply put, if it's the opponent's turn, the cat still faces one certain move against him. Now let me briefly show you the code you'll have to work with. Let's look at the max value function in line 233 of catgame.py. I want to show you where your evaluation function will be called. So that happens in line 246. And notice that we are not simply returning the utility function, but actually the utility function is multiplied by some scaling factor. Now what this scaling factor is doing is giving more importance to levels that are closer to level 0 and less importance to deeper levels. So let's take a look at the utility function. This function starts at line 206, and first we check for terminal cases, in which case we return a value of 100 or minus 100, which mean that the cat wins or loses respectively. And later, if we are not in a terminal state, then we get to call the evaluation function. So here you can see 3 lines that are calling 3 different evaluation functions. The first one in line 216 is a very basic evaluation function I will show you, and this one is called score moves. Next, we have the evaluation function you are about to write, which is called score challenge. And lastly, we have my evaluation function, which is called score proximity. I will tell you about this function in the next video. So when you write your code, please make sure that you are calling the score challenge function, the one you will write. And now let me show you these evaluation functions. These functions are located at the bottom of the source file in a separate class. So the first function is in line 413, and it's called score moves. It simply returns how many valid moves the cat has left. So as you can see, I am simply calling the valid moves function, which returns the list of valid moves, and then I'm returning the length of that list. But I'm returning that length only if it's the cat's turn. If it's not the cat's turn, I'm returning that number minus 1. And why am I doing this? Well, because I'm assuming that the opponent is playing optimally, so the opponent will take the cat's best move, thus reducing this result by 1. And next we have in line 420 where you get to place your code. This is the score challenge function, and you are free to use whatever code you want. Make sure to look around this source file in case you can find useful functions for your code. Notice that I'm returning 1 if it's the cat's turn and minus 1 otherwise. Please make sure to update this line according to your code. This exercise should take you about 30 minutes. When you are done, make sure to look at my solution in the next video. So let me show you my solution. First, I'll update the utility function to use my score proximity function. In other words, I'll use line 218. Now let's see this evaluation function. So my evaluation function starts at line 427, and its name is score proximity, meaning that it outputs a score that is sensitive to how close the cat is to a border. Remember that when the cat reaches a border, the cat wins. So the closer the cat is to the border, the better the score. However, it may be a bit disappointing to you to learn that this function only considers straight line distances from the cat to the borders. So if a border is not within the cat's line of sight, so to speak, then this function will miss this exit for the cat. So with that in mind, notice that the first thing I do is to declare an array of distances, and it's initialized with 2 distances. By the way, I need this list to be of length at least 2. That's why it has 2 values there. So first I get the valid moves for the cat. And remember, I will get a set of possible directions the cat may go. These are west, east, southeast, and so on. So for each of those moves, I am calculating the distance with this dist variable. First I get the cat's location, then in an endless loop, I will increase this distance. Then in line 437, I am actually moving the cat in that direction by calling the target function, and then I'm checking if the cat has reached a border. If it has, then I exit this while loop, and then I check if the cat has reached a blocked tile. If that happens, then I simply multiply this distance by 5. The reason I do this is to accommodate the possibility of going around this blocking tile. So in line 443, we can see that after going in a straight line, it doesn't matter if the cat hit a border or an obstacle, we append this distance into the distances list we have just created. When we are done with all directions, we sort this list in line 445, and finally in line 446, I return a value that is higher if this distance is lower. As you can see, I am subtracting this distance from the game's size times 2. So a lower distance will give us a higher score, and a higher distance will give us a lower score. Now notice that this distance is this whole expression between parentheses. And, once more, this is a conditional expression. I will return the first element of this list if it's the cat's turn, or the second element if it's the opponent's turn. That's why I sorted this list in line 445. So I am returning the best distance for the cat's turn, or the second best distance if it's the opponent's turn. So now let me show you my implementation of the depth-limited search algorithm. First, the custom cat takes this with the DLS flag. We have this at line 92. As you can see, the arguments are the maximum depth and the alpha-beta flag. So let's see this function. So in line 137, we have once more just a wrapper, but now for the alpha-beta function, or the Minimax function. It depends on the alpha-beta flag. And notice that both functions are taking the max depth parameter. So let's see how these functions handle this max depth. And I will show this to you only in the Minimax implementation. You see that the same logic is going on in the alpha-beta implementation. So notice that when we use Minimax in line 296, we are using the max depth parameter with a default value of infinity. That is, dig as deep as you can. But if we send some number there, that will be taken as the maximum depth we are willing to dig into. So let's look at the max value function again. So as you can see, I have selected the depth parameter, and we'll pay attention to the lines where it is used. So notice in line 243 that we are checking if depth equals max depth. So the depth variable is increased every time we call a recursive function. You can see this in line 253. We are calling min value, but with a parameter of depth plus 1. So back to line 243, if we are at the maximum depth, or if we don't have any more legal moves, we are either at a terminal state, or we have reached the maximum depth. So we call the utility function in line 246. So this utility function takes the legal moves list as a parameter. It also takes a flag that says if we are working with the maximizing player or not. For max nodes, this flag will be true. For min nodes, this will be false. Let's see the utility function. You can find this function at line 206. Now notice that this is not just the utility function, but also the function that will call the evaluation function. So here's the implementation. First, we check for terminal cases. If the cat is located at an edge, this is in line 209, then we return the value of 100. That is the greatest score we are willing to give this cat. Next, if the cat has run out of moves in line 213, we will give it minus 100, the lowest score it can get. And finally, we have the call for the evaluation function in lines 216 and 217. Here are my two implementations of the evaluation function. You could comment out either of these to use the other. So one of them is score moves. This function returns the number of moves available for the cat. And the other function is called score proximity, which gives us a better value if we are closer in a straight line to an edge. So let's see this cat working with the score proximity evaluation function. Now that we have the power of limited depth, we can use very small trees and see how long it takes. So let's uncheck alpha-beta pruning first, and let's check unlimited depth. Let's say we want a limited depth of 1. This cat will work very fast. Let me check here. Let me block here. Here. Oh, and what do you know? The cat won. So with a limited depth of 1, this cat made it out. Let's see with a limited depth of 2. Let me try and block the cat. It got out. And as you could see, this cat wasn't taking so long. This cat took 25 milliseconds to respond. Let's take a look at the console window and see how long it takes for the cat to make one move at a limited depth of 1. It took 2 milliseconds. Let's see at a limited depth of 2. It took 35 milliseconds. Let's see what happens at a limited depth of 3. Let me just move the cat. And let's make another move. It took 130 milliseconds. Let's go to a limited depth of 4. There, it took much longer. It took 3.7 seconds. And I'm guessing that's as long as I'm willing to wait. Let's just for kicks try a limited depth of 5. I'm predicting this will be a timeout, because our deadline is 5 seconds. Yes, it got a timeout. So please go ahead and play around with this depth-limited cat. In most games, you have a time limit to analyze the game and think about your next move. Since we have to produce a move before the deadline, we could use depth-limited search, but two unwanted scenarios could come up. We could respond too late, in which case there may be a penalty, we might miss a turn, or lose altogether. We could also respond too early. So early that maybe a deeper tree would have been possible, and thus a wiser move could have been made. The problem is that we have no guarantees as to how long the tree will take to compute, not even with a known limited depth. This is due to a variety of reasons. Some states might have more possible moves than others. We might prune off some branches. Some terminal states might show up earlier than others, and the list goes on. So the question at hand is, how can we make the best use of our time? Here's a crazy idea called iterative deepening. Let's say we have 2 minutes to produce a move. So here's the plan. Produce a move with a limited depth of 2. This might take microseconds. Next, start all over and produce yet another unrelated move with a limited depth of 3, discarding the previously computed move. Then, start over with a depth of 4. Then 5, and so on. And when time is almost up, say 5 milliseconds before the deadline, abort and return the most recently computed move. The logic here is to use the deepest possible tree to produce our next move because, once again, we are more confident with our guess when we use a deeper tree. Think about this strategy for a minute. Does it make sense to you? So here's the high-level algorithm for iterative deepening. I've named the function id-minimax and it returns an action. As you can see in line 2, it's a for loop for a variable max depth that goes from 1 to infinity. And line 3 shows what we intend to do. We are updating a, the action we will return at each iteration, by calling the depth-limited version of Minimax. Here I'm showing a version that uses the maximum depth as an argument. Finally, when the system alerts us that time is almost up, we return the last version of A. Okay, now remember that the problem we are trying to solve with iterative deepening is making the best use of our time. So I'd like you to pause the video and think about this for a minute or two. Is iterative deepening helping us make the best use of our time? Is iterative deepening a waste of our time? Let me further explain this question. Suppose we have this deadline where the horizontal axis is time. Now suppose that computing a tree of depth 1 takes this long, A tree of depth 2 takes this long, and so on for depths 3, 4, 5, and 6. Remember that we don't know this in advance, but notice that a tree of depth 5 could be very well computed in the allotted time. However, depth 6 would take longer, so it's not an option. Now, we might be concerned that applying iterative deepening for depths 1, 2, 3, and 4 would force us to abort the recently started computation of the tree of depth 5, thus returning the solution for depth 4, when we could have made a better use of our time on the solution for depth 5 from the beginning. So once again, the original question can be formulated like this. Are depths 1 through 4 interfering with the best possible solution in the allotted time? Are those calculations a waste of our time? That is the case for this illustration after all. But this illustration is far from realistic. To answer the question, let's look at some data. I'm about to show you some tables that illustrate how the running time of our algorithm behaves as we increase the depth and branching factor of the trees. In order to explain the data you will see in these tables ahead, I'll use the tree I've been showing you from the beginning. We'll see 4 tables with an increasing branching factor of 2, 3, 4, and 5. The tree in this example has a branching factor of 3. The first column will show the maximum depth of the tree. There are 10 rows in each table showing increasing depths from 1 to 10. This example tree has a depth of 4. The bottom level is numbered 3 because we start our count at level 0, but there are certainly 4 levels. The second column will show the number of nodes at the bottom level. In this example, there are 27 nodes at the bottom level. The third column will show the total number of nodes in the tree. This tree has 40 nodes. And finally, the fourth column shows the percentage of the running time that is spent on computing the last tree when running iterative deepening. For this example, the first tree would take 1 cycle, the second tree would take 4 cycles, the third tree would take 13 cycles, and the fourth tree would take 40 cycles. That's a total of 58 cycles. So this last column will show what percentage of the 58 cycles it takes to run iterative deepening in this tree is spent on the last tree, which takes 40 cycles. That's 40 divided by 58, or 69%. Let's look at the first table. Here's the table showing the running time for a branching factor of 2, a binary tree. You may want to pause the video and read the data slowly, but here are some details to notice. First, as we increase the depth of the tree, you'll notice that even for this binary tree, the number of nodes at the bottom level is always greater, and usually much greater, than the rest of the tree above this level. In this table, we can see this by looking at an entry in this column and comparing it to the running time of the previous tree, because that's how many nodes this level will have above it. For example, in a tree with depth of 7, we would have 64 nodes at the bottom, which is slightly greater than 63, the number of nodes above this bottom level. Second, the running time column shows the running time for computing only a tree of depth m, and the next column shows how long iterative deepening would take up to that level. Now the last column shows what percentage this running time represents out of the total time for iterative deepening up to this level. For example, in a tree of depth 7, 127 nodes is a 51.4% of 247, the total number of nodes it would take to run iterative deepening. So notice how this percentage seems to converge to 50%. That is to say that for a branching factor of 2, 1/2 of the iterative deepening time will be spent in smaller trees, which will be discarded. This doesn't look so good, yet. Now for a branching factor of 3, things are starting to look better already. The percentage of time spent at the last tree seems to be 66.7%, or 2/3. This means that 1/3 of the time is spent in computations that will be discarded. As you may have guessed by now, the larger the branching factor, the more efficient iterative deepening gets. Now the percentage of time spent on the last tree for a branching factor of 4 is 75%, meaning that the first 25% of the time will be spent in a discarded computation. Finally, for a branching factor of 5, as you may have expected, this percentage goes up to 80%. So the takeaway is that the time spent in discarded results will be the total time spent in producing the one useful result divided by the branching factor. That's right, although the branching factor is bad for the running time, iterative deepening makes the best out of it because the higher the branching factor, the smaller this fraction of wasted time will be. So back to our original scenario, these arbitrary lengths are only right in that each tree takes longer than the previous one. But the scale is way off. Here's a more realistic scenario for a problem with a branching factor of 5. Remember that in this case, the discarded solutions will take up 1/5 of the total time. So let's say that the final solution for this deadline will be of depth n. Then all solutions of depths less than n will be done in this duration. And the tree of depth n will take this long. Notice the ratio between these two durations. The last tree will take 4 times longer than all previous. So the execution would look like this. Notice how inexpensive the discarded time looks compared to the effective solution. This is indeed the best use of our time when we don't know for sure how long our calculations will take. Yes, the tree of depth n+1 will be interrupted by the deadline, but that would have taken 4 times longer than the time it took us to produce the result for depth n. So even starting with the tree of depth n+1 would have been useless. Now it's time to look at our masterpiece, the iteratively deepening cat. So the custom cat function selects iterative deepening by the ID flag. This is done in line 95. So we call the function iterative deepening cat. So let's see that function. Once again, in line 144, this is just a wrapper for iterative deepening, which, by the way, may be implemented with alpha-beta pruning. And here it is in line 389. So in the first 3 lines, I do some bookkeeping, and the for loop starts at line 393. So here I'm iterating for I in the range from 1 to the size squared. That is, if we are working with a 7x7 hex grid, this will go from 1 to 49. That's because there are 49 possible moves for the opponent. I could have used infinity there. It doesn't make a difference. Now notice that I'm keeping a variable called reached max depth. This is just an optimization in case we have a very short tree so that we know when to stop. So now, in line 395, I'm collecting the best move so far. And as you can see, I am doing this by calling either the alpha-beta function or the minimax function with the maximum depth of the variable I. So now notice in line 396 that I am checking for the terminated flag. This flag is implemented in the alpha-beta and the minimax functions. We'll see it later. So if the last call to alpha-beta or minimax was terminated, we can safely leave this for loop and report the latest best move. If not, it's time to iterate. So in this case, we update the output move with the best move we just produced. We report the best depth so far. And if we never reached the max depth, it's time to stop. That's it. So let's take a look at this terminated flag. Once again, I'll show this to you for the Minimax implementation. And it's the first thing we do. If the time left is less than 5 milliseconds, then we set this flag and we return a failure code, which is -1, -1. Remember, this causes the cat to disappear. But this only happens for regular minimax or alpha-beta pruning with iterative deepening or not. But this only happens for the other cases. For iterative deepening, this means discard this result. So let's go back to iterative deepening. And as you can see, we will not return this best move variable. Look at line 404. We are returning output move, which is a valid move, not -1, -1. So we will report the best move that was legal in the allotted time. So let's see this cat working. Notice that the default here is alpha-beta pruning with iterative deepening. So this is the default cat we want to use. Now, what is the deadline we want? I am using 5 seconds right now. Let's put 3 seconds here, and let's play against this cat. It has 3 seconds to respond. Look at the console and notice that it took 2,995 milliseconds. That is, it responded slightly later than 5 milliseconds prior to the deadline, which is what we coded. Let's try and block the cat further. Again, it responded in 3 seconds. I think this cat will get away. Oh yeah, it got away. Once again, please feel free to play with this cat. Remember, the defaults for the checkboxes have the iterative deepening cat with alpha-beta pruning. So this is the best cat we have so far. You may want to use larger grids, for example 11, which is the one you can see in the online game. And you may even find cases where the cat doesn't play optimally. And that's fine. Remember, we are using an arbitrary evaluation function, something we came up with. We don't have any proof that this is optimal playing. Now I want you to see how well we are doing at our objective of making the best use of our time with iterative deepening. That's why I have written 2 more lines to this function. I just couldn't resist. These 2 lines are 401 and 402. And what I'm doing here is reporting in the console how long it has taken to go through each tree in the for loop. This way, we'll have real data in a running example. Let's take a look. Let me use a 5x5 hex grid. And I will not use alpha-beta pruning, but I will use iterative deepening. So let me make one move. In this example, we were willing to wait 5 seconds for the cat to move. And so notice that the time it took to have our final answer, which was at depth 5, this time was about 3.5 seconds. The rest of the time was spent in depth 6, which was interrupted. But looking at the effective time, these 3.5 seconds, notice how much of that time was spent in the previous depths. That's depth 1, 2, 3, and 4. Those results were discarded. And those results, all of them took 721 milliseconds. That's about 1/5 of the 3.5 seconds. In other words, it has taken about 20% of the whole useful time in producing depths 1 through 4, and the remaining 80% was used in a useful solution. So yes, iterative deepening is indeed making the best use of our time. Now I invite you to do this on your own, trying different dimensions for the game and different deadlines. After some experiments, you'll see that iterative deepening is indeed very efficient. Now I want to show you how good alpha-beta pruning really is. So I'll show this to you by running some examples with limited depth and then with iterative deepening. So let's start with a limited depth cat. Let's say we want a limited depth of 4 and that we will not use alpha-beta pruning. Now notice that I will compare this move with the same move now using alpha-beta pruning. So I will return this cat and this whole game to this state. Let me click on this tile. And the cat has moved one tile to the right. So it took this cat 4.7 seconds. And remember, this is a tree of depth 4. Now let me restore the state of the game. I will edit and move the cat back and restore this tile. Now I will add alpha-beta pruning to my cat and I will click on this same tile. Let's see what happens. You may have noticed that it worked way faster. How faster? Well, without alpha-beta pruning, it took 4.7 seconds. And with alpha-beta pruning, it took 533 milliseconds. That's half a second. Let's make another comparison for yet another move. So let me remove the alpha-beta pruning and I will click on this tile. There you have it. It took 3.2 seconds. Let me restore the game. Now let me add alpha-beta pruning and try again. Once more, it was done way faster. And notice that without alpha-beta pruning, it took 3.2 seconds. And with alpha-beta pruning, it took 369 milliseconds. That's almost a tenfold improvement. You can keep on making these experiments, but alpha-beta pruning is not only good for taking less time, but also to go deeper into the tree. So let me show this to you by using iterative deepening. Let's start a new game and click on iterative deepening without alpha-beta pruning. I will do the same. I will click on one tile and notice that the deadline is 5 seconds. So let's see what happens. There, it was able to reach depth 4. Notice that the cat moved one tile to the right. Now let me restore the state of the game. Let me add alpha-beta pruning, and let's try again. It will take the same 5 seconds, but as you can see, it went deeper. It got to go 5 levels deep. Notice that the cat moved in another direction, a different direction. This is presumably a better informed move, because it has gone deeper into the tree and thus closer to a terminal state. Let's move one step forward. Once again, I will not use alpha-beta pruning now, and I will click on this tile. Once again, it only got to go 4 levels deep. Let me restore the game. Let me add alpha-beta pruning and try again. Whoa, now it went 7 levels deep. So this is the best we've gotten so far. So I hope you could see that alpha-beta pruning showed an enormous improvement in the depth-limited implementations. That's a better running time. The cat responded faster. And also it showed a very nice improvement in iterative deepening by going deeper, many levels deeper. So yes, in conclusion, alpha-beta pruning is indeed worth our while. It's time to talk about further optimizations and improvements you can apply to your algorithms. Here's the first one. Let's take a minute to look at the original functions that implement the max nodes and min nodes in Minimax. Notice how these two functions are almost the same thing, and their differences are all summarized by flipping the sign of the values and functions that change. For example, notice the opposite signs in the initial value of v in lines 3 and 10. Notice the opposite functions in lines 5 and 12. Whatever we maximize in a function, the other one minimizes. So if you are an experienced programmer, you might be thinking that there must be a way to summarize these two functions into a single function. Well, there is. It's called the negamax algorithm. As the name hints, it consists on alternating or negating the sign of a parameter between function calls. Thus, negamax is short for negated minimax. This implementation is based on the nature of the games Minimax applies to. These are two-player, zero-sum games where one player's loss is exactly the opponent's gain. Negamax relies on the fact that the minimum of A and B is exactly minus the maximum of minus A and minus B. So this is what the implementation of a node looks like for negamax. Notice in line 1 that we are using an additional argument called color. This can be +1 or -1, and it will give us part of the sign flipping behavior we want. Line 2 shows that we will not just return the utility of a terminal state, but instead its sign will depend on the color of the node. That's what determines if we are at a min node or a max node. The remaining lines use the same logic as max value, but look carefully at line 5, where we use the negative return value of the recursive call of negamax. And we send the negative version of color, effectively flipping the role of the whole function to implement min nodes or max nodes. As you can see, we don't need the label of min node or max node, so all negamax calls are simply nodes. Here are some additional details you may want to know about negamax. First, it applies only to two-player games. Although Minimax can be used for multiplayer games, where you would model everyone else's turn with min nodes and your turn as a max node, negamax is designed to alternate between min nodes and max nodes, so it only applies for two-player games. Second, it works with all the optimizations of Minimax. You know, alpha-beta pruning, iterative deepening, the works. Third, negamax does not provide a significant running time improvement over Minimax, so don't get your hopes up. This is not the reason to use negamax. So what's a good reason to use negamax? Well, it's a matter of taste. Negamax is said to be more elegant than Minimax, and yes, it provides some saving on the stored program in the end, but the savings are just the size of the min value function, say less than 1 kilobyte. Now, a good reason to know about negamax is that you may find code set to use Minimax with alpha-beta pruning, limited depth, and other optimizations, which is actually written with the negamax logic. So, when you are reading someone else's code, it's important to know that deep down, negamax is doing the same thing as Minimax. Another useful improvement for Minimax is a transposition table. It's simply a cache of previously seen states. This is sometimes known as memoization. An entry in this table contains some representation of the state and the resulting utility value. So when a node function is called, the first thing to do is to look up the state in the table. If it's found, we may confidently use the utility value from the table and return. And if it's not found, we may proceed with the usual recursion of Minimax. So for example, this is what a transposition table would look like for chess. It's a table where each entry contains some representation of a state and the previously found utility value for that state. It makes sense to keep highly repeating states in that table, and the lookup function must work fast because, as you may imagine, this table can get crowded very fast. This may sound like a very good optimization, and it is, but it's not perfect. It has some complications. The first one being, it has the potential of requiring to store all possible states. So how much memory is that? Well, that's in the order of O of b to the m, the same as the running time. Remember how the running time requires longer than the age of the universe? Well, this storage would require more entries than there are atoms in the universe. So we need a reasonable fixed size to implement the table. And we also need a replacement policy when the table becomes full. These policies tend to favor states at levels close to zero, as they would save us larger subtrees. All of these complications are typical in the implementation of a cache. So these have been highly studied in operating systems. Let's go back to the limited depth problem. By now you should know that evaluation functions are tricky to get right. That's because we don't really have a clue of the actual quality of our functions. These functions are usually based on our own speculation. So here's a clever idea, which is sometimes called a Monte Carlo evaluation function. Suppose we are at the maximum limited depth and we need an evaluation value. Instead of calling an arbitrary function, we could keep on playing the game by making a random move, then another, and another, and so on, until we reach a terminal node. In this example, it's a winning scenario of value plus 100. But we don't have to stop there. We could play another sequence of random moves for both players until we get a terminal node again. This example shows a tie. That's a value of 0. And so on, we could do this several times. This time we got a losing outcome of minus 100. In this other sequence we got minus 100 again. And in this final sequence we got a winning outcome of plus 300. After getting a number of results, we could average these utility values to report our own evaluation. In this case, the average is 40. So here are some details about the Monte Carlo approach to evaluation functions. First, it's based on statistical, but very real and accurate data. Nothing is speculated. It's the result of a simulation. There are studies that have shown that this approach performs similar to Minimax in average, and that's great news. This approach does not hurt the recursion because these sequences of moves are performed in the same game, so the space complexity of this function is O of 1, or constant. It only needs one state of the game to run a whole sequence. This approach also has a cheap running time because it does not run the whole remaining subtree. It just goes some levels deeper for each random sequence. That means that its time complexity is O of m. That's linear time, which is always good news. Now, this approach only works when terminal states are guaranteed to show up. We might take a long time going back and forth before we run into a terminal state. If that's possible, some precautions must be taken. Well, that's it for the course. We've gone through a lot of material, and there's so much you can still do to keep on learning. Here are some ideas for your next steps. Have fun with the code. You may try evaluation functions to see if you can get the cat to play better. You can also give the Monte Carlo evaluation function a try. Now, I understand that tweaking someone else's code can be difficult and tiresome, so you may want to implement a game of your own choosing. There are several frameworks you can use to create an intelligent agent that plays chess or Go, which are among the most competitive games where your new AI skills can be useful. And you know what? There's much more to AI than game playing. One of the hottest topics today is machine learning, where you can get a computer to learn from data and then solve problems with the knowledge it has acquired. While technically an application of machine learning, artificial neural networks are also fun and definitely worth learning about. You may want to look into search algorithms which have been used in virtually every AI application. In fact, Minimax belongs to the category of adversarial search algorithms. Finally, cognitive systems are changing the world. These are intelligent systems designed to perform the functions of the human brain. A well-known example is the IBM Watson system, which has won the first prize at the TV show Jeopardy! And lately has had several useful applications, like customer service and medical assistance in diagnosis and treatment. Speaking of cognitive systems, Jill Watson is a very bright teaching assistant in a cognitive systems graduate course at Georgia Tech. Jill is, among other things, an IBM Watson system.